Hello and thank you for joining us today. In this video, we will introduce you to the concept and benefits of Virtual Time Sensitive Network, or V-TSN for short. Unimore, the University of Modena and Reggio Emilia in Italy, present this video. We are researchers from IPERT Lab, the high-performance real-time system laboratory of Unimore, as well as IPERT SRL and Minerva Systems, the two spin-off of IPERT Lab. Our research focuses on the next generation of embedded computing platforms and autonomous systems. We have a variety of autonomous vehicles, such as 5 self-driving cars, a laser-gate vehicle, delivery bots, aerial and underwater drones. We also participate in autonomous racing competition, such as the Indy Autonomous Challenge. We are a team of about 70 researchers and developers with a funding of 10 million euros. In the IMOCO project context, our goal is to provide expertise in real-time system deployment, developing our virtualization solution as well as deploying it on real-life systems. We are the leader of BB4, Real-Time Smart Control Platform, the building block that provides technological solutions aiming to enhance compute-intensive workloads at the edge using virtualization for performance and real-time guarantees. We are involved in Demo 2 and Pilot 3 inside IMOCO. Demo 2 is about smart sensoring on injected plastic parts, and Pilot 3 is about high-speed packaging. We provide integration platforms and deployment environments for both projects, as well as our expertise on sensor data collection and transmission for Demo 2. In addition, we offer our skills in enforcing timing guarantees and in virtualized environment with and without TSN for Pilot 3. Now, I let my colleague continue the presentation.
Hi everybody, we have designed, implemented and partially evaluated this component called Virtual TSN. As the name suggests, it implies the use of virtualization techniques and time-sensitive networking protocols. On one end, the virtualization allows to have different operating systems running on the same platform, and as a result, it grants better isolation between the system's applications. Moreover, virtualization can also optimize the distribution of the hardware resources so that, for example, if we have a board with 4 cores, we can have one virtual machine that is using 1 core and another one executing an EV task, let's say, with the 3 cores. This makes the system more flexible since you can add more resources to one virtual machine or add another virtual machine. But also, thanks to the isolation properties, greater predictability. On the other hand, TSN protocols make Ethernet communications predictable, enforcing the timing guarantees also for the Ethernet networks. But also, it can manage mixed critical traffics by assigning a priority to each of them, improving the overall network stability. Virtual TSN can be used in different industrial sectors, from the automotive one to the avionics, rhythm, and so on. We can use it when we have highly connected clusters with different electronic control units and chiplets connected that require low latency and high-speed communications. Another point in favor of the use of virtualization is that it can also help to reduce the power consumption and costs, since we don't need to buy another platform if we want to add a feature into the system. Moreover, we can leverage the flexibility of TSN networking also on rigid scenarios. Our solution wants to use a single TSN endpoint shared among multiple virtual machines by still preserving the determinism and predictability. For the industrial automation, virtual TSN can serve as a software-defined central control unit. In fact, the new software components can be deployed simply as new virtual machines or into virtual machines. So we don't need, as I said before, we don't need additional hardware nor link. This also optimizes the cost and the hardware usage even in constrained environment. Moreover, we can leverage virtual TSN also for making inter-virtual machines communication predictable. So let's see how does virtual TSN work. Virtual TSN runs in a dedicated virtual machine acting as a backend and is composed of two components: the virtual switch that allows the communication between front ends, so the other virtual machines, and the Ethernet port, so with the outside world. Since we also need to apply a TSN policy, we have also a scheduler that implements one of the possible TSN protocols, such as IEEE 802.1 QAV and QBV. Remember that TSN usually requires to assign a priority to the Ethernet flow. So QAV is a credit-based shaper, which means that we can assign a credit to a flow. And this credit usually represents the percentage of the maximum Ethernet bandwidth that we want to reserve to a flow. For instance, an Ethernet communication usually has a speed of 1 gigabit per second, and if we have two flows with different criticality, we can give 70% of the bandwidth to the high critical one and the rest for the other one. QBV instead is a time-aware shaper that assigns a time slot to the flows, and the flows can send messages only during the time slot. For instance, in this case, we can set up it so that each 100 millisecond period, in the first 60 millisecond, we can send only one flow with high priority and the other 40 milliseconds for the other one. In the picture, we have the red blocks that represent our V-TSN solution, where we have the TSN scheduling algorithm, the virtual switch, so the logic that controls the communication with the inside and outside world, and then we have the Ethernet driver that manage the Ethernet port and the inter-WAM driver that manage the communication with the other virtual machines. So in order to have the virtualization, we need this component called the hypervisor, and in this case, the communication with the other virtual machines is based on a shared memory mechanism. So using this inter-WAM shared memory mechanism, virtual machines are able to pass message to the virtual switch, and then the virtual switch is able to understand if the message is for another virtual machine or if it needs to go outside. We actually support different types of operating systems like bare metal application, real-time operating systems such as Eric Enterprise v3 and Linux systems. Moreover, we are able to run more than two virtual machines simultaneously, plus our backend. While for our backend, we were able to reach high bandwidth with the bare metal driver, while maintaining a high scalability. In fact, we can add virtual machines or delete them during the execution. For our experiments, we have used the AMD Xilinx Sync UltraScape Plus 102, which has 4 main cores, ARM Cortex A53, and 2 real-time cores, ARM Cortex R5. For now, we are only using and considering the A53 cores. Our solution is based on JLabs hypervisor. JLabs, by definition, is a type 1 hypervisor that allows the assignment of hardware resources to virtual machines in a static way. And since we are using a platform with 4 cores, 4 is also the maximum number of virtual machines that can run on it. On this platform, I mean. So our experiments use one virtual machine that is running our V-TSN and up to 3 virtual machines for the Ethernet flow generator applications. In this box plot, we are showing the latency results of our solution in different scenarios. For this evaluation, we have used the ping tool and we are sending 100,000 packets with a 1 millisecond interval. The scenarios in this case are Linux on JLabs, so without V-TSN, and then the solution with V-TSN and a variable number of virtual frontends. In order to also have a comparison with other state-of-the-art and famous hypervisor, we compared our solution with Xen. As we can see, our solution performs better than Xen-based solution. It has low latency values, but also reacts better when multiple virtual machines are communicating. For the bandwidth evaluation, instead, we use the hyperv tool. The picture here represents the maximum bandwidth that we were able to reach when executing more virtual machines simultaneously for both TCP and UDP protocols and in both solutions, our and Xen-based solution. Also in this case, our solution, the red box, is able to split the maximum bandwidth correctly. So as we can see, the experiment with only one random virtual machine and the experiment with 2 and also 3 virtual machines split the maximum bandwidth correctly, and also it outperformed Xen, especially when we talk about UDP protocol. As future challenges, we would like to port our V-TSN to a real-time core. So, for example, one of the Cortex R5 present in ZCU102. In this way, we may leverage all the A53 cores only for the front ends and use only the real-time cores for the backend, so for the V-TSN. Moreover, we will also like to support different platforms like the NVIDIA one and to implement additional TSN protocols. Just to provide you an idea of where we are going to use the V-TSN, the V-TSN was involved in the design pattern of a dual zone architecture for autonomous driving use case, which is described in the time-sensitive autonomous architecture paper. In this paper, we have designed and evaluated the importance of the utilization of TSN protocol in a real-time application like autonomous driving systems. In this paper, we evaluated this using both simulated environments, but also in a real car, and the car that was used is a Maserati Quattroporte. The design of this architecture involves different technologies such as virtualization, V-TSN, real-time operating system, different kind of DTS also. For the iMoco project, I leave the word to my colleague.
We are working on developing our solution for iMoco to apply V-TSN in industrial scenarios that require high determinism and high acceleration with virtualization. These will enable us to create a robust and flexible network that can support various applications and devices in a secure and efficient manner. Our goal is to leverage the advantages of V-TSN to enhance the performance and reliability of industrial systems and processes. Our solution, presented on the right, is composed of edge computation nodes that embeds AI application, denoted on the figure with NVIDIA and Huawei, that communicate via TSN networks provided by SOCI platforms, with the camera, sensors, and actuators from the ZCU102, which implements our V-TSN solution. All the data produced is also sent via the TSN to the fog server, where is located a digital twin of the system. For more details, here are the resources used for making this video, such as our paper on time-sensitive autonomous architectures, as well as the link to the various TSN platform providers' website, one for Soki and another one for Aurelia, and a link through the Jalaus projects and the link of the website of a spin-off Minerva system. Thank you very much, and we hope that this video suits you well.